Hi, good morning. Actually, the first couple talks this session I think have set up pretty nicely what I'm going to be trying to talk about, and then also I think Beth's last question is really pertinent to what we've been trying to do. So this is it's been a collaborative effort between Sprue Canada Limited, which is a commercial spin-off of the University of St. Andrews, as well as Anna Redden's research group at Acadia University. I apologize a little bit for the slightly dramatic title. Part of what I was trying to convey is that these are very challenging sites, and certainly the site that we've been working at in the Bay of Fundy is extremely challenging, as was alluded to just the other day. The main objective of the study, and I think why it's maybe somewhat complementary to what Jamie's just been talking about, is using passive acoustics to try to understand when Harbour porpoises are using tidal sites and what's really driving that, and then from an effects perspective, trying to measure the variability in use or detection rates in these sites. So the background, I can pretty much skip this slide. Just remind us again of why we're doing this, why we're interested in terms of collision, reef barrier effects, and acoustics disturbance. I guess the one thing I'll point out, the data that we've collected maybe doesn't inform collision quite as directly as what some of the work that Jamie has been doing, although I think hopefully I'll show you that we do have a better understanding of when and why these animals might be in these sites. So we're working up here in the Bay of Fundy and the far reaches of it in Minas Passage in the fourth site, which is shown here in this rectangle, and that's the acronyms here: Fundy Ocean Research Center for Energy, I think. Yes. The site here, in terms of our study design, we've got 7 sea pods that are click detectors, so they're not recording raw acoustic data. We had our units spread out from, basically the bathymetry goes from the shallower areas up here at this North 1 site at about 25 meters down to the deepest site here at South 2 at about 85 meters. And then we have these sites here are roughly between 50 and 60 meters, so similar depths. Just to orient you, when the tide is flooding, we're moving from left to right, and when it's ebbing, we're going from right to left. I think I got, yes, that's left, so I got that. We collected 2 years worth of data usually from May through November in 2011 and 2012, and combined between all 7 sea pods and the multiple deployments that we had to do, right, because we have to refresh the deployments or pick them up and redeploy them every 3 months-ish or so. We got a total of 1,342 days of data, which I think is fairly good sample size. Just so that you know how we deployed these units, or I say we loosely, this is Anna and her team. We've been deploying these from the back of fishing vessels. You can see here the sea pod. Here's the hydrophone on this one end. It's actually fastened inside these sub buoys, attached to a riser that was usually about 2 meters in length, and then it has this other large chain, which is basically just a weight to keep it in place. So those were brusquely tossed off the end when they hit the GPS points for those locations. In terms of the analysis, as I've mentioned, sea pods are detectors and don't actually record the raw data. Once you've retrieved the data, you then have to run it through the classifier in the sea pod software. Just to sort of highlight, you do get some other data or noise in there. So this top display is just showing you changes in interclick intervals for these clicks that are known as what we call weak unknown transient signals. So we don't really know what they are. but they're typified by this change, this long, nice increasing change in inter-click interval. But I just point out as well that we also have recorded some of the VEMCO tags that Anna and her team have been putting on other critters in the Minas Passage. And I apologize, you can't really see that. I can see it on my screen. It's a porpoise. It's a series of porpoise. It's a click train of porpoises that has a changing amplitude and also a decreasing inter-click interval as the animal is presumably coming closer to the units. Just as an estimate of our false positive rate, we think that we're getting about 7% false positive rate, and typically those are woods that get misclassified as a porpoise echolocation click. In terms of our statistical modeling, we looked at a series of covariates in our model. We used a GAM and dealt with p-values with a GE because we have temporal autocorrelation in our data set, right? We're basically, in essence, continually recording in the same spot. In terms of spatial autocorrelation, I think in terms of our study design, I think we've dodged that bullet in the sense that our pods are about 700 meters apart, so beyond twice the range of what we think a C-pod can detect. Just briefly, pod ID. So some of these we didn't include in the model either because of singularities or collinearity. For example, temperature wasn't included because it's collinear with Julian day, as you might expect. And when I say Julian day, that's loosely speaking. We're not really counting the days from whenever it was in 2000 BC or whatever when Julian calendar started. It's the day of the year, so 1 through 365. Other ones are self-explanatory. I'll explain this one, area, because this is the forest development site. We were somewhat interested in as well as whether there was a difference in detections inside and outside of the forest site. We couldn't test that because of singularities. Click max has to do with one of the settings on the C-pod. You set how many clicks per minute it actually will record, and that's an attempt to try to not run out of memory space in your 3-month deployment. Typically, we set them at 96 clicks per minute, but you can also set them to the next higher up is a ludicrous 65,000 clicks per minute, and we did play with that. So that's what I mean when I talk about click max. Percent time lost. Because you set the total number of clicks per minute that the unit will record, when it's filled that buffer, it stops recording for the minute. And you can measure that as a percent time lost. And the reason why I put sediment noise in here, and it feeds back into the earlier talk this morning on sediment noise, is that actually there's a lot of noise in there from sediments. And so that's what that one is. Day-night index, I'll show that later, but basically the length of our days changed quite a bit in the northern end of the Bay of Fundy, so we wanted to standardize that so that we were comparing the middle of the day in terms of day length instead of just a clock time. The others are self-explanatory. So in terms of results, thankfully, so I'm presenting these results, these GAM plots, in terms of in order of priority. In terms of I'm presenting the ones that were significant covariates in predicting or rather what was driving the porpoise detections. I'm presenting them in order of importance. So thankfully, as one would expect, because this is what we would expect in an area where the habitat is used seasonally by Harbour porpoise, the largest signal was indeed from seasonality. The reason why I've done this gray-hatched area is that, well, we actually don't have, you can see from the rug plot on the bottom, we don't actually have data in the middle of the winter, except that Anna's crew has just managed to, they braved the winter elements and collected some winter data just this past winter, so I'm anxious to see that data to see how that'll affect this trend. So I would completely discount this hump here. I really don't think that's there. I think that's just a fact of this. We had to fit a circular spline to this because at 365, you go back to day one, right? So I think that's an artifact, but it'll be fixed shortly, hopefully, with the new data that Anna and her team has collected. The next important covariate was tidal velocity, and I think what's interesting is that, well, in this site in Minas Passage, okay, you see that we get higher velocity, this in meters per second. We get higher velocity flood tides, so a flood is a positive, ebb is a negative, and we get our highest detections, porpoise detections at sort of moderate flood tides. And likewise, so the next covariate of importance was tidal height, again in meters. And again, you see our highest detection rate is occurring at moderately high tides. In terms of location, if you remember sort of the X pattern there, the locations for our different sites, you do see, and I think this is, I would interpret this as this is driven by depth. So we have our lowest detections in our shallowest site at about 25 meters, and our highest detections at our deepest site. And then intermediate detection rates at these sites that are about the same depth. I'll talk a little bit about East 2 in a little while. And then diol patterns that we often see in a lot of places where we stick CPODs out. We'll see that detection rates are highest at night and lowest in the daytime, which is another reason why sometimes visual observations are very difficult, because that's the time when you'd expect to see, I guess I should take that back, because they may just be switching from clicking foraging behavior to visual foraging. So forget that comment. But anyway, so what we see is our highest, so 1 is midday, 2 and 0 are midnight. So just before midday is our lowest point, and our highest point in terms of detections is just before midnight. And this is the bedload noise, and so it is an important covariate in there. And basically what happens is, as the velocity in these sites increases, you start moving sediment. And the higher it goes, the larger the sediment you can move. And the sediment starts dinging together, makes a lot of noise, and it gets actually picked up as clicks. And it completely swamps the signal, so that at some points, at highest tidal velocities, you record very little bit of time. And you can see, as you would expect, that as the amount of that minute that you record is actually decreasing, you, as you would expect, have fewer porpoise detections. So what this is telling us, that highest tidal velocities, we are really going to struggle ever to say anything about porpoise presence in those states. The good news is, even though this is a really challenging site, 75% of our data has set 25% time loss. So we're mostly working in this area. However, this is, you could argue, the points where we're actually most interested in, right? Because that's when tidal turbines are going to be doing their most work. And just to sort of show you how this happens at this particular, in one location and one deployment, I think this is over a month period or something. You can see that the percent time loss from the sediment noise really starts kicking in at about 1.5 meters per second, either on the ebb and the flood tide, but it is more strongly related to the flood tide. And this really shows this to you. And the reason I bring this up is that even within a tidal site, there's going to be, as Caroline just said, that there's going to be a lot of spatial heterogeneity in terms of noise and sediment load. And that's why I mentioned East 2 here. East 2 is a site, in essence, that we abandoned, because there's no reason to monitor there, because you're not going to be able to tell anything about that site. So if you're setting up a survey in a tidal site, I would highly recommend doing short-term deployments, so that you can quickly recognize these sites and abandon them before you put too much effort into them. But at these other sites, you see these nice, so this is, percent time lost on the y-axis, and you can clearly see the spring and the neap tides, and you can also see the flood and the ebb tide. So you're getting a different signature on just from percent time loss. So you could actually probably use this to measure, I don't know, tidal velocities, sediment transport, but I don't know. So location is important. So in conclusion, I guess to tie it back into sort of the, I guess the ecology of the systems and these physical covariates is that I think that we are getting closer to trying to understand when and how these animals are using using these areas on a broader scale. And I guess I would argue that because we get a signal. That's my 15 minutes, according to my timer. Sorry about that. If I could remember my code, then I can stop this. That's the timer. Cancel. Thank you. Yes. All right. Wasted another 15 seconds. I won't do that again. So I guess in terms of the physical parameters, I think it is really important for us to understand what's driving porpoise presence in these areas. And because we're getting a signal where we're seeing mostly on a flood or a flood tide and flood velocities, my guess is that that's not the direct physical parameter that we actually is driving that presence. I think it's likely to do with turbulence or shear or something that's concentrating their forage fish or reducing the escape options for those forage fish. And so I think it's heartening to me to see other folks working with birds and marine mammals in these sites and fish as well, starting to think about turbulence and shear and upwelling and these other things that are of importance. And I guess I'll just iterate mooring, design, location. I can talk a little bit more about that later if people have questions. And I'm out of time. Acknowledgements, funders, and folks who've helped out.
Thank you.